Okay, I made some slight adjustments to the coil that used to have the battery and the switch. And what I've connected it to is a function generator, and that's going to make a ramping current up and down. You can kind of see that right there. It'll be a little noisy, but you can see the red line going up and down, almost linear. Okay, and then what I'm going to do is I've got a second coil here. You see it's about 400 turns, and we'll measure some of the dimensions. I think we need the cross-sectional area of that thing. But what I'm going to do is I'm going to stuff this down inside, and I've got some little blocks down there to keep it right at the center. And what we're hoping is that the function generator will send a current that's varying in time to this outer coil. We'll pretend it's a solenoid, and we'll use the solenoid equation, the number of turns per length, and the manufacturer says that's 3,400 turns per turns on the thing. So N, capital N, is 3,400. Let's measure the length over which those turns are oriented, and it looks to me to be just about over 9 centimeters. So the turns per length is 3,400 divided by 0.09. That'd be little n. Big N is 3,400, 0.09 meters. Okay, and let's see, what else do we need? I think we need the cross-sectional area of this thing, because from the turns per length, the current, the permeability of free space, we can find the magnetic field, and then the rate of change of the magnetic field, if we know the rate of change of current for the big coil. But what I think I need is what's the cross-sectional area of the little coil. And you know, I'm going to go with about 3.5 centimeters. It's kind of squarish, so we'll say it's 3.5 centimeters by 3.5 centimeters. All right. And I just lost my little clip right here, so I'll put it back on. Stuff that back down in the electromagnet, making sure nothing's touching other than what I want to be touching. All right, and let's see, that should be set up to go right here. And what I should just be able to do is hit collect. And yep, we can erase and continue here. All right, and what you should notice, as noisy as it is, I have an upward current here, and then I've got it ramping down here, and I got it ramping up, ramping down, ramping up, ramping down. And every place the current is changing here, I see a constant electromotive force. When it's coming down, I have a positive electromotive force. When it comes up, I have a negative electromotive force, and it's almost like a little sawtooth for the electromotive force, which is generated as the rate of change of the current, which is going to the outer coil, takes place. Now, a couple of things I want to show you here. We'll save this for you. Okay, this is good data. You can see that I'm getting somewhere around, that's 0.05, about 0.02, maybe 0.03 volts positive, 0.02-ish, 0.03 volts negative. You want to make an average measurement of what that peak is, and you got to get the slopes on these two. And I'll show you how to do that here in a bit. I want to change a couple things though, just to show you the effects. The first one I want to do is I want to take just a piece of iron, okay, and I want to insert it right here, not touching anything, it's just stuck inside the hole of the little coil that's in the center there. I just stuck that thing right in there. And now I want you to watch, I haven't changed anything else. I've made no adjustments to the rate of change of current. I've made no adjustments at all. And if I hit collect, erase and continue. It's off scale on the bottom. Let's see what happened. Let's auto scale the bottom. And I said it was something like 0.02, 0.03 volts. Well, now it's well over 0.1. It's like 0.11, 0.12-ish. Okay, and getting a much bigger voltage merely by putting this thing in. One of the things you should notice, it's not as squared off as it should be. We talked about a resistor and an inductor, and we showed that the current and the voltage will build up over time. And I think that's exactly what I have happening here. So I have that exponential buildup. It takes a while because this coil has some resistance and it also is an inductor. And so we're seeing that exponential buildup. A couple other things I want to do. What if I want to make the voltage that I'm generating even more here? Well, one of the things I could do is I can come over and I can increase the rate at which these ramps are occurring. So let's do that. Let's basically double it. Let's take it up to 20. Nope, that was too much. Hertz. Let's double it, 20 hertz. And should be good to go. And let's double the current, double the rate of change of current. Erase and continue. And you see it's going up and down faster, and I have to auto scale the voltage again. The electromotive force that's generated gets even bigger. Now it's up about 0.2, but it's not doing real well and making it kind of squared off. All right, here's the next thing I guess I want to do. What if instead of these ramps going up and down in current, what if I turn the current to a sine wave? So let's do that. Let's stop doing a ramp up, ramp down with all that noise on it. And I've taken it to a sine wave, and still pretty lousy looking on current, but you can see the voltage being generated here is a sine wave when I put a current that is changing sinusoidally as well. Okay, the purpose of this part of the video is to assist you with doing the data analysis from part C of lab 9. And what you should remember is we had two coils here, a big one, that one had 3,400 turns on it. Okay, we're pretending it's a solenoid, and so we can use the solenoid equation. And the function generator was supplying current to that big coil, and that's being shown here in red. And I know it's pretty noisy, but I made a quick theoretical sketch in the lab handout, and I want to show you what I think. Let me do straight lines here. Let me draw what I think you should be seeing here in this red curve. I think if you draw a line, it kind of goes like that to a peak up here, and then it comes back down this way to zero somewhere around here, and then it goes back up like this, and then it comes back down like this, etc. Okay, and that's probably enough, so you get the idea. On the other hand, this blue curve, now, as I said, this was the I need to switch over my template for drawing here. This was the 3,400 large coil. Inside of it, we literally shoved in a small coil. It had 400 turns. And while this current was being sent to the big coil, it was changing the magnetic field. And remember, the magnetic field for a solenoid should be something like B is equal to the permeability of free space times the number of turns, that's 3,400, divided by the length of the thing, and I guess I'll use little l, sometimes I use big L, times the current. And so if the current is changing, as we see here, pretty much linearly is what I'm trying to show, then the magnetic field will change. Well, of course, one coil is inside the other, so any change in the magnetic field of the big coil will cause a change in the flux sensed by the small coil, and the electromotive force down here should be equal to the rate of change of that flux in time. Okay, and so I guess if we can find the rate of change of this current from the slope right there, we can find that, and you can see I've got all kinds of opportunities to do that. Okay, I should be able to put that right in here, find the rate of change of current, find the rate of change of the flux of the field, the magnetic field B, and that's the same magnetic field that is in the flux we're talking about here. I just have to find the flux by taking this magnetic field from the big coil and multiplying it by the area of the small coil. And that would be through one loop of the small coil. And then I usually tuck the N right in there, so it looks like National Basketball Association. Okay, that's the total flux through the small coil, because I'm using the area of the small coil, and that's what I'm seeing changing in time. Okay, and if you think about it, if this is a straight line right here, it has a constant slope, and that ought to yield a constant electromotive force. And I think I'm seeing it right there. If you look straight down here, okay, those 2 points line up, and I hit the wrong button here, sorry, coming right back, and those 2 points line up right there, and that's roughly the electromotive force that is the constant electromotive force associated with that linear changing current, which is giving me a linear changing magnetic field. And the same thing's happening here. The slope is the opposite, and so right here the electromotive force is right there, again corresponding points right here. And if you come up to this point right here, that would be where the current switches direction. And it happens to be exactly at the point where the electromotive force is zero, because at that exact instant, there is no change in current, there is no change in magnetic field, there is no change in magnetic flux, and there's no electromotive force right at that point right there. And in principle, this would be kind of what's called a square wave all the way through. But remember, when we were talking about RL circuits this morning, we said, these things don't change instantaneously. They go through what we call an exponential buildup. The shape of that curve is 1 minus e to the minus t over tau. And I think that's what you're seeing here for these electromotive forces. Each and every time the electromotive force tries to change in that coil, I get a shape like this, because certainly the coil has inductance, but because it's made out of real wires, it actually has real resistance. And so that's what we're showing here. All right, time to take data now that we've talked through this. Okay, so I guess I'll get rid of this guy. I don't need annotation anymore. There's several places I think I can do the linear fit on the top curve. And so I'm going to highlight a region right here. Okay, and then I'm going to hit the linear fit button up at the top. And what's this right here? That one didn't do anything. I'm going to get rid of this one. I don't even know if I did it. And you can see my fit line is pretty darn close to that red line I was approximating with my cursor before. And if you look, I get a slope right there of about 2.2 amps per second. Let's try a few other places, like maybe that increasing voltage, linear fit. And over there, I'm getting about 2.28 right there. Okay. And let's see, we've got 2 positive slopes. Let's pick 2 negative slopes as well. And so we'll go right about here, for example. Okay, linear fit again. And over that range, oh, that was much less. It is fairly much parallel to that line I drew. Okay, but it is highly dependent on where I put these brackets, what data points I'm actually sampling. I'm trying to work through the noise here, minus about 1.82 amps per second. And let's get this out of the way a little bit, do one more right in here. Oh, right to about there, do a curve fit. That looks reasonably good. Okay, there's the box. And I'm seeing about 1.95 negative again. What I would do is I would average these 4 numbers. Okay, I'm just guessing. It looks to me like they average out to be around 2.1, maybe 2.05, something like that. And that is the rate of change of current that goes in step 4 of part C of lab 9. Okay, and then you work that calculation through as I described here. That would be the rate of change of current here. So if I multiply it by N over L and mu 0, that would be the rate of change of the magnetic field in the big coil. That's the one with the 3,400 turns. So that's what you're using for N, and I gave you L as well. Okay, I multiply that by the rate of change, I'm sorry, I multiply that rate of change of magnetic field by the number of turns in the small coil, that's 400, and multiply by the area of the small coil, and that should get me the electromotive force that I'm measuring, okay? And those two pieces of calculation, I think, should be done in step 5 and step 6 of part C to lab 9. Okay, and so that's what we would call our predicted electromotive force. Let's actually make a measurement, and I've got about 5 of these little areas to choose from. Let's come right through here, okay? And this time it should be flat. It should be, I'm expecting it theoretically to be a flat curve. So instead of doing a fit, I'm going to use statistics, and I'm really interested in the mean, and the mean looks like 0.022 volts is what I'm getting right there. And let's do the same thing over this range right here. Okay, do statistics, and I get an average value of about 0.0235. Okay, and I can do the same thing right over here. And I'm trying to use that region where it's fairly steady. Okay, and I've got this thing blocking. I've got a little pop-up toolbar in Macintosh that's causing me not to be able to get to my toolbar. So I think if I do, there it is, it went away. Came back. It thinks I want to talk to it. Give me just a second here. There we go. And if I sneak on in there, I can do statistics on that segment right there. And that time I got 0.0244 volts. And let's do one more, and then we'll see we've got 4 data points from each curve. Stats again, and that time I get 0.0237. Pretty reasonable. I would average those 4 numbers, and that is the measured electromotive force, and I think that should go in step 7. Now, I think I said this in class today. This prediction that you did in step 6, I think is going to be pretty much, it's going to be substantially bigger than 0.026, 0.026, 0.026. In fact, when I did it, I had it over 0.04, okay? You may find you have it even higher than that. The question, I guess, is what is wrong with our model that caused the predicted value to be almost double what the actual measured model is, okay? And that's an important piece of science because there are some issues with our model. This equation right here, for example, for a magnetic field for a solenoid, it assumes a pretty long solenoid. And so the question, I guess, might be how long is long? How big does L have to be in order for this equation to be valid? I'll let you look that one up. It's actually in our textbook. But the answer is pretty long, and maybe ours wasn't long enough. Okay, we assume that this magnetic field here is a constant everywhere on the inside of the big solenoid. Is it? Is it maybe bigger in the center than it is closer to the outside edge of that cavity that is the inside of the spool that the wire is wrapped around that makes up this coil? Could be, and maybe I was a little bit off center with the smaller coil. Truthfully, it had to be in order to fit in there with all the wires. I can guarantee you they weren't exactly concentric. I tried as best I could, but that's what they were. How about the area? Is the area that I've got here actually correct? Are there some coils that are substantially smaller than this area that I used? We used just one number. I think we said use 3.5 centimeters. There are certainly coils on that smaller coil that are much smaller than that. And there are probably some that are bigger. And so perhaps 3.5 centimeters squared, because we were turning it into an area, perhaps that's too small a dimension for the average coil that's in the turns that are on that spindle. Maybe I picked a number that was too big. I measured something that was real, but I don't know if it was representative of that coil. All right, I think I've given you some things to think about. Perhaps you can come up with some other ideas, but those are certainly reasons that would contribute to this voltage here being significantly smaller than what you predict.